Hello, my name is Bowden Ingebretson, and this is a video explanation for Lab02 in ECE 275. In this lab, I implemented Boolean expressions using Quartus, and then verified them using Model Sim, and proceeded to build a full adder circuit in WALC-WE to explore Boolean logic in real time and better visualization. The main objectives were to determine whether two Boolean expressions produce the same output for all input combinations, and to reinforce Boolean logic concepts through different circuit designs and visualization. So firstly, I was given these two Boolean expressions here. F1 equals A or B and C prime, and D or A and C prime, or B and D prime, and F2 is basically the same thing. F2 equals A or B and C prime, and D or A and C prime, or B and D prime, and A or C and D. Both the expressions take four inputs A, B, C, and D and produce a single output. Our goal is to determine whether F1 and F2 are equal. And then we were also built to make this circuit here. This was designed to, I also designed I'll show you later, but I designed a truth table to verify with the F1 and F2. But basically here you can see that the best way I can go about showing these is that A goes through here, this is an OR, and these are able to produce those parts in the F1 and F2 equations. And you kind of see that when I click on these, it kind of stops at this halfway point, and we kind of make these parts, and then we kind of put those parts together here and here. And the NOT gates are used to produce C prime, which then gets added into these ones, this one, and then we also produce D prime, which was used here. And basically this circuit was designed to produce those two equations, F1 and F2, and here are the outputs at the end. And you can see F2 just has the extra part here from the F1 equation. Then I simply put it in the model sim, and model sim really helps us look to see if they're equivalent. Right here at the bottom we have F1 and F2, and if they're equivalent they'll have the same values every time. And they often are equivalent. C0, 0, 0, 0, 1, 1. And here's my truth table that I was talking about, A, B, C, D. You can see it's a little bit hard to read, I'm sorry about that, but F1 and F2 are not always equivalent. We can look at that here too. So when A is 0, B is 1, C is 1, D is 0, F1 is 1, but F2 is not. Same here, A is 0, B is 1, C is 0, D is 1, F1 is 1, F2 is 0. So through my model simulation, they're not equivalent. F2 and F1 are not equivalent. Literally one of these could be incorrect and not the same, and that'd prove to me that they're not equivalent. Then I was tasked with designing a WALC-WE, sorry if I'm pronouncing that wrong, simulation. This is a full adder design, and here's our truth table with all zeros. Now, so basically if you click on this using my keys, or I think you can actually click on them, but I'll be using my keys 1, 2, and 3. This produces, this is A, B, and C in, and then this is sum, this is C out. So let's assume this is like 1, 2, 3. All my keys, and then S and C out. So with all 0, none of these are lit up. These are both off. Let's try this one right here. C in is on. C in, sum, correct. Okay, B, how about just B, sum, yep. How about B and C? Should be C out. Okay, and then just A should be sum. Yep. How about A and C? It should be C out. Yep. How about A and B? Should be just C out. And if they're all on, both of them are on. So that shows that the circuit and the WAL key are put together right, according to the PDF I was given. Basically, the sum output is sum equals A, X, or B, X, or C in. and the carry output is equal to A and B, or Cn and X, or A, X or B. This circuit takes three inputs, A, B, and Cn, and uses the XOR and OR gates to compute the full adder outputs. And this is a dip switch here to produce the truth table that I'm flipping through. And the LEDs are just really helpful to visualize indicators of what's going on, and it really helps you see how these circuits work. This circuit doesn't help verify F1 or F2. We already did on the other one. This is simply just a different design to help see and look at stuff visually. The full adder it's actually a really good example of how Boolean expressions can be used in real-world applications like arithmetic operations inside of processors. And this has a lot of real-world application, and I just thought it was really interesting to look at after this lab. And in conclusion, course model sim, I confirmed that F1 and F2 are not equal, meaning they do not produce the same outputs for all inputs. And my well-key full adder circuit allowed me to explore more Boolean logic in a different way with a different design system, and also allowed me to visualize how real-world arithmetic circuit functions. Some final thoughts I have: this lab reinforced my understanding of Boolean algebra, digital circuit design, and simulation tools like Quartus Model Sim, and it's my first time ever using Wowkey. Thank you for watching, and please let me know any questions you have.